So good morning, everyone. Welcome for this last lecture course. So last time I introduced the model that we're going to study today. Essentially, the spirit of this model is the following. We have a spatial structure, which we approximate by a graph, and here it's going to be a fully connected graph. And so here we have a fully connected graph. So that's space. And with the all-to-all spatial couplings. And here, at the nose of the graph, we have local interactions. Of the several type. And the last ingredient that we have in the model is locally environmental noise. Which is independent across species and across spatial locations. So let's say that we have few sites. So alpha going from 1 to q, or just alpha beta to label the siting indices. And some dynamics that I had written like last time was the following. So for the population size of species I at site alpha, so we have these local interactions, simple, no disorder in the interactions, with again the simplest interaction matrix, plus, how did I write it? Okay. The environmental noise, and then the diffusive coupling between the different sites.
Why are there double connections between some nodes?
Oh, that's what did I do here? No, sorry. Pay attention. So here we have this equation. We're gonna. So the convention is autonomous, and the correlation function of the noise is just Gaussian white noise. So that really, if you look once more, so last time we had studied this part, just the model in isolation, or d equal to 0 or q equal to 1. And now we're adding this spatial coupling. So what I wanted to say is that this equation is fairly reminiscent to the one we had derived through dynamical mean field theory for a single species when there are disordered interactions, except that in that case, the noise or the correlation function of the noise has to be self-consistently determined, and here we're imposing that it's self. In order to, so, and what we will do is that we will study the model in the limit s goes to infinity, many species, and q going to infinity, many sites. And the order of limit is first s going to infinity and then q going to infinity.
One general question. So, почти корректная это symmetric interaction.
Yes.
But local operator, typically you have friends. Asymmetric.
Yeah, I agree.
The way I call it local operator.
Okay, it's okay. Not ultra-tight in the sense that the local dynamics is n dot is equal to n times something that is linear in the n. So it's a special choice for the interaction matrix here, which is the simplest choice and which is indeed symmetric.
Local operator of few species have very different sort of phenomenology. For two species, they kind of limit.
Yeah. Okay.
Limit cycle because actually there is integral of motion, infinitely many, but isolated. And over there, somehow noise would bring you more or less from one or the other.
No, you're right. You're right. So, but that's what we're describing, which is in the original Bloch-Cabot model, is some kind of, I mean, it's the result of a fine choice of the interaction coefficient. So, in the more general form, what I call Bloch-Cabot type is really n dot equal to n times something linear. But these cycles that we're talking about are fragile to the addition of. When you have some terms that are zero, and if you put them non-zero, you break this phenomenology. And so, as before, for the single site dynamics that we studied last time. So I'm going to introduce the following quantities. New I alpha, which is S n I alpha divided by m alpha, where m alpha is the total, let's say, total biomass site alpha. And I'm also going to introduce epsilon hat, which is epsilon s divided by sigma squared, b hat is d divided by sigma squared, and tau, which is t sigma squared. And first, I will work in the case where this is fixed when s goes to infinity. So if you go here, but that's convenient. But if you go here, that means that effectively, as you pack up more species, the strength of interaction with your conspecific is much, much larger than the strength of the interactions with the others, and that stabilizes the system. And then we'll see what happens when epsilon hat goes to zero, thus recovering what's really happening in that case. So after a couple of relatively straightforward manipulations, you can express the equations of motion in terms of these variables. plus P gamma alpha So this is the set of equations that you get. Essentially, the dynamics for the relative abundances, which are here, is pretty much the same, except that now you have a Lagrange multiplier that enforces, as you can read here, that 1 over S, 1 over I, mu I alpha is equal to 1 everywhere. Then you have the dynamics for the total biomass. And then this is just a value of the Lagrange multiplier enforcing this constraint. And now, essentially, what you see is that, I mean, the different degrees of freedom for the i's, the different species, here are coupled only, I mean, this is nu I, this is nu I, this is by I, nu I, nu I, so they are coupled only through the gamma, which contains all of them. But then as S goes to infinity, this just converges to, I mean, you can show it tools like DMFT, this converges to the mean of nu psi and nu square. So effectively, you get a decoupling between the different degrees of freedom as S goes to infinity. Here's a decoupling of the different degrees of freedom corresponding to here different species. And we reach the state of full coexistence, meaning that everyone survives. I mean, they are all equivalent here with the symmetry of the interactions. Full coexistence, where for every species, we have this effective equation. And now gamma is not given by this sum, but just by averages over the realizations of the noise.
Why do you write brackets? Why don't you write P and beta over M alpha?
Okay, so you're right. What I want to say at the end is that, okay, you expect to reach a state that, but you're right, it's M beta over M alpha, it's the same thing. You expect to reach a state where that's going to be spatially homogeneous. So that, and this quantity, in the same way that gamma alpha becomes deterministic in the large S limit, this quantity, which features gamma alpha, also becomes deterministic in the largest limit. So this converges to a constant across space, just diffusion and this anyway non-conservative term. So M alpha converges to a constant, and so eventually M beta minus M alpha divided by, I mean, M beta minus M alpha will drop in the steady state. But okay, you could also say that M beta divided by M alpha is equal to 1, and that would be the same thing. Figure.
kind of many examples we would have with something, for instance, large in space, large in time, and then this Steven limit, and you don't just write x going to infinity equal, you also write x divided by root of constant. So somehow here you have f going to infinity and q going to infinity. One may assume maybe something interesting happens. But the ratio of f divided by root of q, the other way around, something like that. But there are no such Steven limits.
I mean,
Because S and Q both going to infinity.
So that's a good question. I would say that in this simple example, no. And the main reason is probably the underlying geometry of space, which is fully connected. But at least there hasn't been any evidence of a crossover behavior that would happen.
For example, when you replace gamma alpha by a constant, that's for S going to infinity.
Yes.
Not Q.
That's S, so far that's S going to infinity.
We will study the mode of the limit.
Yes.
For the moment being Q.
So for the moment, Q is finite. Q is finite, time is finite. And then we'll send Q to infinity. Okay.
If you take Q equal to 1, you're back to DMF.
I mean, it's not even DMFT because interactions are completely. I mean, there's no disorder in the interaction. So it's the simple, this model, when epsilon is equal to 0, you can map to the realm we studied last time.
I don't understand the statement you wrote. At infinity, there is a decoupling of the degrees of freedom.
Yes.
Are what is the coupling? Are the species?
Yes. So the different degrees of freedom have different species. Yeah.
No, sorry, I misunderstood the difference.
Okay.
I thought the degrees of freedom were different from species.
No, corresponding to the different species. So in the steady state, so we expect gamma alpha is equal to gamma, m alpha is equal to m, independent of the position. And for Q going to infinity, you have the same thing that the dynamics, I mean, it's once more, it's fully connected in both species and space, so that's why it happens like this. You have a decoupling between the different spatial degrees of freedom because essentially they are only coupled for the mean. And so the dynamics of the different sites is described by mu tau equal to mu gamma minus epsilon at m mu psi with z hat 1 minus nu as so mu is equal to 1 going to the symmetry between species. Because here all species are completely equivalent. So in the steady state, the mean of nu has to be equal to 1 for any species. So this is the limiting dynamics. And that's in Statistical. And as I was saying, the interesting thing is when epsilon hat goes to 0, meaning we're restoring a regime in which the strength of the interactions with your conspecifics is not so different from the strength of the interactions with the different species. And what we find is that, so because there you can analyze the corresponding steady state, I mean, you can write the steady state distribution associated to this. So this, when epsilon hat goes to 0, we find that it goes to 0, which is the quantity which is here. And now you just have here, gamma is the correlation of nu with the noise, plus the noise. And this is written in Statistical. So if you rewrite the equation in the Ito convention, this will just cancel out. So we get d nu d tau is equal to nu psi plus d hat 1 minus 1. And this equation is nothing but the extension to the fully connected lattice of the equation governing, or the equation for the partition function of a directed polymer in a disordered medium, which is like derivative with respect to time is equal to, if the partition function is called z, z times spatial temporal Gaussian white noise plus diffusion. And so now we can write the steady state E of nu, which up to proportional constant partition function. Yeah, sorry. Nu minus 2d hat divided by E minus d hat divided up to normalization factor. And so that's, the behavior is very different compared to the one when, let's say, Q is equal to 1, so when there is just one single site, because the distribution of the nu in that case, so we could compute the distribution of the nu at finite epsilon hat, but the limit when epsilon hat goes to 0 did not exist, meaning that you couldn't get coexistence of many species unless epsilon hat was finite, meaning that intraspecific interactions were much stronger than the mu, which is the strength of interspecific interactions. And that constraint is relieved once you add a spatial structure, at least in this fully connected framework. Here there is a limiting distribution.
Sorry, I'm not practiced with Ito and Stratonovich. I mean, physically, are they equivalent? It's just a choice of how to say representation, and finally the physical quantities are the same, or they are a physical choice.
Let's say that. I mean, I would say it's the first one, because basically, if you have a stochastic process of the diffusion type, you can represent it or its evolution, the Fokker-Planck equation, right?
Yeah, but they differ.
Which is unique and well defined. And corresponding to a Fokker-Planck equation, to a given Fokker-Planck equation, you can write a Langevin equation. And if the noise is multiplicative, you need to specify the way you interpret the Langevin equation. So Ito, Strato, you have more general discretization for that. And so for a given stochastic process characterized by a given Fokker-Planck equation, you can write an equivalent Langevin equation in Ito or an equivalent Langevin equation in Strato. They wouldn't look exactly the same because of the difference in the convention. But once you do calculation properly, you would find that all physical observables have to coincide. Okay. Okay, so now a few remarks.
And it's easy to derive the steady state. Just write the steady state, because it's easy to derive it from this equation.
Yeah, because you can write the Fokker-Planck equation, and going. I mean, the Fokker-Planck, going from the Fokker-Planck to this is fairly easy. There's nothing really fancy in there.
For instance, if you take moment of new sufficient kilowatts, it will diverge.
Exactly.
Is it obvious? Not obvious from equation itself.
What do you mean?
How you interpret the fact that sufficient kilowatts moment of new diverge?
I mean, it's this power law, which encodes the fact that sufficiently large moments would diverge, typically encode the. So maybe that's one way to interpret it. Typically encode the amplitude of the largest degree of freedom in your system, because originally you have to think about the fact that per site. So this is the per site distribution, and per site you have actually S species. So this power law will set the scaling of the maximal fraction of the biomass which is occupied by the largest species. And so this fraction is indeed a power law of the number of species.
The U can sum to 1? Oh no, they sum to S.
No, so here the average of mu is 1, but because they've been rescaled. So the mu sum to S. But the fact that I mean, as soon as 2D is strictly positive, you would see that the maximal occupancy is less than S. I mean, scaled sublinearly with S. So no one can really take up a finite fraction of the biomass in that case. But the fact that so what we'll see, what's really important, at least for the rest of this presentation, is that the variance diverge past the threshold for D. These too small, the variance is going to diverge, and this has strong physical consequences that I will explore later.
For instance, some other examples, when you really go to something infinite, you get divergence, but then you want to interpret it, for instance, a large moment diverge, and then you remember that your Q or S, whichever, something Q, for instance, is finite, and then you find that actually divergence means that actually the moment is finite, but it's Q to some power. And in that sense, when you go Q to infinity, it diverges. And sometimes moment they have interest in giving some interest in power, and in many even simple processes, even simpler than yours. For instance, what they exhibit, starting when they diverge multi-scale. For instance, it's not just scale with Q some power and power if you have, I don't know, power with mu, I don't know, M.
Yeah.
It would be not just Q to some power M minus X, but it's actually more complicated function. And many simple examples like that, and so you can probably figure out, how it is. Is it interesting? I don't.
No, I agree. So I don't think this has been done. Yes. So the first thing I wanted to say is that there is coexisting state even when epsilon goes to 0. It's characterized by broad abundance distribution. Looks like this with a cutoff at around 1 over 2D. That's the exponential cutoff, which is here. And for 2D less than 1, the variance, what we were discussing, the variance mu square is finite. And for 2D, 2D larger than 1, and for 2D smaller than 1, the variance diverges. It is not defined. Okay, so far that's the picture. And it turns out that we can get a bit more of a mechanistic picture, which will be helpful later on. So we have locally the dynamics with, we have the dynamics for the N with local interactions, right? Plus diffusion and all that. It turns out, as I explained, that what we can compute is an effective generalized Lotka-Volterra equation for the spatially averaged population size. So once you cause grain over space. But when you do that, the coefficients are going to be renormative. Of the G or G, the generalized Lotka-Volterra coefficients. So to get the mechanistic understanding of the full coexistence state, one can show that there exists an effective force grain Lotka-Volterra equation for Ni bar for the spatially averaged population sizes. So Ni bar is equal to 1 over beta, not 1 over q, sum over beta and I beta. And how can we show that? The fact that we have an effective dynamics for the Ni bar comes from this coarse graining can be achieved by noting that the Ni bar, mu I bar, so same thing, 1 over q sum over beta mu I beta, become flow variables when epsilon hat goes to 0. And essentially, this is a consequence the marginality of the epsilon equals 0 dynamics. So here, if you go back to essentially, if you go back to this equation, when epsilon hat is equal to 0, but now you say that, and I'll show it a bit more details, but just the sketch of the idea, you say that this is really, what you have here is really nu bar. Then you can just divide by nu bar goes away, and this dynamics conserves, by definition, the mean. So the resulting dynamics that you get to leading order, when epsilon hat goes to 0, conserves the mean. And so the mean becomes a flow variable, effectively.
No, the word renormalization is most of what theoretical physics. And, I'm not sure that what you mean by renormalization.
It's not renormalization group, but effectively what I'm going to do is to integrate out over the short scale degrees of freedom to get a coarse grain description. So there's no renormalization group here. You could call it coarse graining. At least that's specifically what I'm going to do here. And that's in that sense that I'm using. Okay. So here, essentially, I mean, you have to divide by nu bar to make nu bar go away. So to show that the dynamics of nu I bar become slow when epsilon hat goes to 0, one introduces the quantities xi alpha through the nu I alpha is equal to nu I bar times xi alpha. So it's how much you deviate, but in a multiplicative way from your mean, special mean.
That's not about lecture. I recall that. As I remember, CO2 monitor, it was here most 600, then 700, now it's 1200.
It was 900. There was nobody in the room.
Exactly.
It doesn't work.
Exactly. So the problem doesn't work. It was really, I was talking to Kirill, telling that it's totally crazy numbers.
It's 1,200 plus minus 300. Well, minus
1500, that's already, very bad for yourself.
My interpretation is that there is a rat behind, blowing into the sensor.
Just look at it. It's totally crazy.
Should we open the door just or?
Sorry. No worries, that was a good point. It was worth noting it. Okay. So then once you do that, after rabbit transient, that corresponds to the equilibration of the total biomass. we obtain that so you can get an equation for xi alpha. It's just going to depend on UA bar. Where this is a spatial average. So that enforces the fact that when you sum now over I, you get 1 for the xi alpha by definition of here. And then you have the dynamics of mu I bar, which is epsilon hat m mu A bar times one over S sum over J mu J squared xj squared minus mu A bar. And what matters in this expression is this factor here, which is very small when epsilon hat goes to 0. So effectively, when you look at those variables, which is just a fraction of the average population size, they equilibrate quickly, and they adiabatically follow when epsilon hat goes to 0 the dynamics of mu A bar. So the dynamics of the degrees of freedom adiabatically follows that of mu A bar. And under short time scales, you get that the distribution of x for species I, it's the distribution across sites, is given by x minus 1 minus 2d plus 2 epsilon hat m gamma I mu A bar times epsilon exponential minus 2 epsilon mu A bar x minus 2d divided by x, where gamma I imposes the fact that the average of this guy is 1 and is nothing more than the variance of x. And so
What is this new date? Is it all this new? This is for us. For instance, when it comes to the U or the I of X, they all have small x essential singularity. They win extreme and
no,
extreme and so all derivatives will be able to be
no, it's not. I mean, to me, there's nothing obvious. I mean, I wouldn't say it's obvious, it's a recurring property of these models when you have multiplicative noise. Essentially, it's a consequence of, if you look at this, and then you add something where this is small, that's typically what you get. Where this would play the cutoff. And yeah, exactly. This dynamics is a log Brennan motion.
When you say that the dynamics, if it follows, means what?
So given that this evolves on very long time scales, at any instant of time, it's legitimate to consider that, and you'll see why I'm doing that, that the distribution of this guy is the steady state distribution of this equation at fixed nu A bar. And so now when epsilon goes to 0, you can compute this quantity, which is the variance of x. And so when 2D is larger than 1, even when epsilon equal to 0, that's what we saw before, this distribution has a finite variance. The variance can be computed, and it's this. Diverges at 2D equal to 1. And it's a bit more tedious to give the correct scaling when 2D is smaller than 1, and this will diverge with epsilon. But to the leading order, you get this. minus 1. Where K, I'm not writing it, but it's order 1 as epsilon hat goes to 0. So it's just a constant that involves essentially the d hat times epsilon hat nu high bar to d minus 1. I'm also putting m here because it's going to be convenient later, but of course it could be absorbed in the redefinition of the constant. So this diverges when epsilon hat goes to 0. And it's a power of nu A bar.
At the moment, you didn't do any normalization.
So no, there is no, so there won't be renormalization in the sense of renormalization group. It's just simple coarse graining. And so,
did you do a coarse graining? No.
Not yet, it's coming.
So could you do a kind of multiple time analysis by introducing 2 times and all these kind of multiple scale methods that x varies on the time scale epsilon tau or is that what you're going to do more or less?
No, so now what I'm going to do is to rewrite essentially you can write the generalized Volter equation at or the equation of motion at the at the site level. Then you can average over space. And what we'll see is that the average over space actually features the variance of the x. And this is what you need to compute in order to get an effective description on these large scales. It turns out that, because of this separation of time scale, the variance of the x at any given time, past this rapid transient, is given by a function of the nu A bar. So it's given by the coarse grain population size. So then you can close the equation at the level of coarse grain population sizes. So the equation was the following, where d n I alpha divided by dt is equal to n I alpha times 1. Yes. R sigma squared. So this is Thibaut plus 1/2 plus psi I alpha, so this is Thibaut, plus psi alpha minus epsilon plus mu divided by sigma square n alpha minus mu divided by sigma square sum over j different from I and j alpha plus this diffusive term ni bar minus ni. And now what I want to do is just to sum over alpha, which corresponds to looking at the time evolution of the mean population size across space. So the diffusion term drops. Because this is Gaussian-wide noise, as q goes to infinity, the variance of this term when you once you sum goes to 0. So that goes away. We have epsilon plus mu sigma squared sum over beta ni beta squared minus mu divided by q sum over beta sum over j different from I ni beta and j beta. But what we said is that the first thing that we should is that the dynamics between the different species decouple. So this term is actually nothing more than mu ni sum over j different from I. Once you take the spatial average, ni bar and j bar. So here there's nothing fancy. I mean, the structure of this term just carries through. Same thing at the coarse grain level. But this guy is going to behave differently. And if I introduce these notations, namely with the nu I bar, you would get m squared nu I squared divided by q s squared over beta x beta squared. And so now we have to compute the variance of the xi. And as I was saying, we've shown that the variance of the xi is a function of the nu I bar, which is itself up to proportionality constant ni bar. But then we can compute this and obtain an effective equation for ni bar. So first, for 2D larger than 1, and for epsilon hat going to 0, we have, so this we said is 2D divided by 2D minus 1 to the leading order. And that's already instructive. So we have the ni bar is equal to ni bar times r divided by sigma squared plus 1/2 minus epsilon mu divided by sigma squared 2D minus 1 ni bar minus mu sum over j and j bar. And this is larger than 1. So if you remember what we had said when we looked at exactly this model, we're saying that there is a full coexistent fixed point, etc. And the condition for the stability of that fixed point was that the intra-specific interaction term was larger than the inter-specific interaction term. Otherwise, the fixed point is not stable. And what we see is that hence here at large scales, there is an increase of the effective intraspecific competition compared to the coefficients in the local field.
The last term is really new, not mu over sigma squared.
It's mu over sigma squared, sorry.
For dimensional reason.
Yeah.
We're comparing them. Actually,
Here, and carries here. Thank you. Thanks. And in fact, the coexistence fixed point, yes.
Because when you go to epsilon plus r goes to 0, then epsilon original is going to 0 or it's 0 kind of. Written now again epsilon plus mu. Should I write? I will get rid of epsilon.
So here, okay. So what I was doing is epsilon hat is epsilon, where this is the original guy, at sigma squared.
Yeah.
And I studied the behavior at epsilon hat finite, meaning epsilon of order s here. And what I'm saying is that I'm extending the results. So when epsilon hat goes to 0, you get this. You can do this, and this step you can do. And then I'm replacing epsilon hat with its value in terms of epsilon when epsilon is finite. It turns out that it works. But I agree that there is something a bit like I'm taking something to infinity, then to 0, recovering the original scaling. So I agree.
Yes, also part of the what Pirey was asked that if you have like more generic, some I don't know, ODE or PDE, but okay, in your case maybe more complicated because of stochasticity. You have small parameter, and so naively you just say small parameter equal to 0 if you have something, and then you use regular definition. So in interesting cases, it's actually not good. For instance, if your parameter in front of large derivative, they are known to boundary layer. Or if it's not, but if for instance your time is very large, it could be some circular term. In that case, maybe you have what he was referring to multi-time technique is actually like more universal from which you can derive the and WKB you can derive. But generally, just regular perturbation theory isn't good. And in your case, is it like philosophy more generic?
So it's not, because what we'll see, what we're interested in is the variance of this guy. And if you do regular perturbation theory to the leading order, you find in the interesting regime where which I'll come, you'll find that this term is infinity. So here, at least at that level, even though I'm not going to multi-time analysis, at that level, regular perturbation theory fails. And that's why you get this. I mean, here, what we'll see essentially is that you get anomalous scaling for the term in here. It won't be linear anymore in N. But coming back to this simple regime, what we find is that, so you want this term to be larger than this guy. So D helps is stable provided that epsilon is larger than minus mu divided by 2D hat. And here we have to compare to the condition epsilon larger than 0 for the single site dynamics. Now we can go to the more interesting regime for 2D less than 1. We get instead that, so we need to inject this, and this will give a new I bar 2D minus 1 with new I squared. That will be a new I bar 2D plus 1. And then we're going to take out a new I bar as a multiplicative factor over here. So what we get is this. dni bar over d tau is equal to ni bar times r sigma squared plus 1/2 minus mu to the sum over j and j bar, that doesn't change, minus k, let me write k prime, also order 1 times ni bar to the power 2 d hat times epsilon plus mu. And now the theory inside the parentheses is not linear in the abundances anymore. So we have an emergent non-analyticity of the self-interaction term. And this connects to, so I'm just giving the name, connects to the theta logistic growth equation that sometimes has been used on phenomenological grounds, and which writes n dot is equal to n times r minus n to the power theta. So that's at the single species level. And that's interesting because it tells us what happens in the presence of disorder. Because here I did everything in order to be able to do some analysis in a way that's not too involved. I took this simple form for the interaction matrix of the local theory. So written here. But now you can ask what happens in the presence of disordered interactions. So more general setting. And I'll conclude with this before the break. And so here, let me stress that this non-analytic power comes from the fact that the variance of this distribution for the nu is divergent. robustness to the presence of disorder. And this is the main result, I would say, from the paper that I quoted last time. I'm just rewriting the IPhT-TV 2026. So consider now dni alpha over dt is equal to ni alpha r minus epsilon plus mu ni alpha minus mu sum over j nj alpha plus sigma interactions sum over j a ij nj alpha okay. So here we have disordered interactions. Let me put it Z to be consistent with Zij n01. And here, previously when doing DMFT, we had studied sigma scaling as 1 over square root of S. That was the condition in order to do DMFT. Here I'm even taking sigma ant of order 1. So this is a very strong interaction scaling where in the absence of noise and in the absence of space, you would expect to be deep inside this sort of Maillard phase of heteroclinic cycles. And for 2D less than 1/2, so they showed that the state of full coexistence persists, even in the presence of disorder, even in the presence of, so let me say a strong disorder because it deviates from the 1 over square root S scaling with which you can do DMFT. And in fact, they did pretty much the same thing. And here, so at the coarse grain level, they obtain pretty much the same equation that we derived. Minus mu and j bar. So there is no coupling from I also and j bar. So this term, which is interspecific, just you can take the spatial average in a straightforward way. And now you get the same renormalization or the same non-analytic renormalization of this guy. Thank you. We have. So d divided by sigma squared. And so first, as s going to infinity, the coexistence this point is given by ni var, so is r plus sigma squared divided by 2 divided by mu s 1 plus some small quantity. And now if you want to look at the stability of this, its stability can be investigated by looking at the spectrum of, so it's something that we did before, Jij. So we have sigma and Dij, the interaction parts. But now we have the self-interaction part, which is k prime, epsilon plus mu. N bar, that's the coexistence fixed points. 2d minus 1, delta Aj, and there is probably a 2d also. So we still have, as before, the competition of this term, which is the disorder term, and that the broad spectrum grows as square root s. So if I plot the spectrum, so let me plot something like this. So if I plot the spectrum, so let's say that the interactions are asymmetric, so that you get the circle. So this is square root s, but now what you have to look at is the competition of this with respect to the self-interaction term. And this guy blows up because n bar scale is 1 over s, and because of this non-analytical power, this behaves as s to the 1 minus 2d. So here we have s to the 1 minus 2d. And so if 2d is smaller than 1/2, essentially this diagonal component runs away faster than the circle grows, and stability is ensured. So it's the same kind of argument as with respect to May, but behind it there is a phenomenology or a mechanism that could explain why the self-interaction term would grow, and so that would counterbalance what you would naively think from the accumulation of the circle. Okay, and I will stop here and we can have a break.
come.
Okay. So for this last chapter, the generic scale invariant in many species coexistence, I wanted to take the opportunity to, given by this class, to discuss some work that I did recently, which hints towards what might be the generic behavior of those systems once you are in finite special dimension. I should say that the conclusion of this are, I mean, it's on the archive, but there is just, I mean, it's just the beginning of the study of these problems. So, okay. So now what I want to study is the following. So the starting point is the stochastic generalized Lotka-Volterra equation with S species and diffusive dispersal in dimension D. Then I want to write like dt and I xt is equal to ni times gi xt minus ni plus di Laplacian ni plus the demographic noise square root 2 ti eta I xt, and this is eta. And with, so gi is ri minus sum over j alpha ij imply alpha ij. And so that's a Lotka-Volterra form for the growth rates gi. And also, so these are independent spacetime notional events. And for simplicity, even though it doesn't change much of the results, I'm going to assume that Ri, so all the one body parameters, I'm going to take them all the same. So Ri is going to be equal to I for all species, and it will be equal to 1 by redefinition of time and population levels, rather. Di is equal to D, and I'll take it equal to 1. And then Ti is equal to T is a number which is the same for all species. And so there is the interaction term. So disordered interactions asymmetric with and I'll take the weak scaling regime, which is mu over s sigma divided by square root s zij with zij unit variance 0 mean Gaussians independent, which corresponds to gamma is equal to 0 in the notations that we had previously. Okay, that's the set. And the first thing that I want to look at is what happens when you have no interaction. So, I mean, that's something that we discussed directed percolation. We briefly discussed last time with no interactions. So that's sigma equals 0, mu equal to 0. So in the absence of interaction, so that's I'll write it, put it equation 1. The dynamic of each species follows 1 with, so it's just GIXT is equal to 1. And as we discussed during lecture 4, there is a critical noise strength, TC, such that, so for T smaller than TC, Ni bar of T goes to N bar star, which is strictly positive, as T goes to infinity, where Ni bar of T is the specially averaged population size. T larger than Tc is like Ni bar of T goes to 0. So the population goes extinct. And the critical point belongs to the directed percolation universality class. And so in the following, what I'm going to take is that in the following, we assume that T is smaller than Tc, so in the original setting that is here, ensuring the survival of a finite fraction of species.
But in this simplest case, of course, it's simple at all.
It's still not simple at all. The properties of the, so I use the properties that have been known from numerical simulation about this universality class.
Yeah, but for instance, nobody knows analytically TC.
Nobody knows TC.
Then
It
you
exists. No.
But from that maybe easy stuff.
Yeah.
Fine.
Yeah, exactly. Nobody knows the critical exponents. When we have estimates, very good estimates. Numerically. But no, it's still surprisingly complicated, I would say, for a one-dimensional problem, even in one dimension.
Is there a mathematical proof of the existence of the two phases or something like that? Or it's just a matter of question? Can rigorous works? It's such an old problem.
I would
Also, this guy he wrote about even book contact process, this mathematical guy, not Bramson, but from UCLA. So, better guesses.
Oh, he's very famous.
Yeah. He has a book called.
I can't pinpoint to any reference now, but I would say that yes. I mean, because the thing was introduced as an anisotropic generalization of the percolation problem and has been studied by mathematicians. So maybe what's missing in terms of the proof is the fact that this actually field theory belongs to the same universality class that I don't know. But the problem of directed percolation as a geometric problem has been studied. But and maybe there is some. I don't.
I already argued, but still again, why always take this noise being not correlated with tree, but Boston space, and why not just
For this one. So for this one it makes sense because it's this is really saying that the the birth-death events that are stochastic events between the different individuals are essentially independent across individuals. So for the death, for instance, each individual carries a clock. When the clock rings, the individual dies, and okay, the distribution of those times is given. But individual base, they are independent, and that naturally leads to something that is not correlated in space and time.
what I said? It's actually could be very well independent. Exactly delta x minus x prime, but independent. Because, for instance, in some fertile land, it's actually good to reproduce, and in some
Yeah.
So
it's
not so good or in axis.
So I agree, but that would be more about environmental noise. So you would say that what would make sense in your case.
You're right. Proportional to n. I agree with you. Proportional to n.
Ri is a function of x.
Yeah. You're right.
Because you have heterogeneity in the landscape. And the only thing I can say is that for now I'm neglecting this. I think that the mechanism that I'm going to present is fairly simple. So I think it would apply also to that case. But then the detailed properties would depend on the critical behavior in the presence of quenched noise. And that is more complicated. Because in the presence of quenched noise, the directed percolation universality class in any dimension is destroyed. Okay. Okay, actually, let me erase this board so that I keep the proof. So the dynamics converges towards that you can see it in numerical simulations. The time translation invariant steady state. And it's characterized by the set of especially average population sizes j equal 1 to s. Okay. So now if I look at the growth rate of any species, in that steady state, can be decomposed into the spatially average parts and fluctuating parts. So it's GI XT, you can write it as GI bar plus delta GI XT with the GI bar is 1 minus sum over J alpha ij and J star, and delta GI XT is sum over J alpha ij and J XT minus NJ star. And now if we send S to infinity, we can use dynamical mean field theory once more to get an effective description in terms of a single field. So when S goes to infinity, dynamical mean field theory provides an effective description in terms of a single field. That I want to write like dtn is equal to n g bar plus delta g xt minus n plus delta n plus square root 2 tn by xt. And that is the same argument as before. This, so alpha I0, alpha I1, all of them are independent. So this is, and the different degrees of freedom are weakly coupled, because it's like the coupling is 1 over square root s. So this is a sum of many weakly coupled or many weakly correlated random variables converges to a Gaussian. So this is a Gaussian variable in the DMFT picture. And this is a Gaussian process. And as before with dynamical mean field theory, the whole game is about finding the first two moments. I mean, this one is zero mean. But it's about finding the mean and variance of this one and the correlations of this guy. But you can write, so the equations for this mean and variance are provided by DMFT. And so what you get is that, so if you look at the mean of G bar, it's 1 minus. So if I take this to be mu divided by S, I have 1 minus the average of n bar. which I can write as 1 minus mu times dg bar, dg bar. This is going to be equation 2. And so the spatial average here I can replace by averages of this equation at a fixed j bar. So it's an average over 2 at fixed j bar. Pg bar is the distribution of this random variable. We have j bar squared, which is sigma squared d g bar Pg bar times n g bar squared, which is strictly positive because the finite fraction of species survive. Yeah, it's connected. Yeah. And now we have the equation for the correlation function of this guy. So let me write first that Pg bar is just the Gaussian distribution 2 pi g bar squared c exponential minus 1 of g bar minus g bar divided by g bar squared c. And so we have an equation for the correlation function. Delta j x t delta j prime x prime t prime is equal to sigma squared dg bar p g bar times nxt minus nj bar. It's the average of the deviation with respect to the means, and xt prime minus n g bar. And that's as a fixed bar. And here, let me write 2 again, because I will need it in this box. And that's 2. So in general, I mean, this equation, this one especially, needs to be solved at all scales. So, I mean, analytically, the problem is not tractable. One cannot get an exact solution for this, or at least we don't know how to do it. But still, something that can be shown is that the solution to, so that I'm going to call 3, necessarily displays scale invariance at large scale. So emergence of scale 3 correlations. So,
Question.
yes.
So technically, how to gain some intuition here? For instance, if you have some simple but interactive process, and so you very easy to write some mean field for that process, some of this process. And the rule of thumb is that this mean field is totally wrong in small low dimension. And actually, the most difficult dimensions often one. And then sometimes in 2 it's almost correct, and then 3 is correct, so you can use it with for low time asymptotic in field. But that is doesn't work. And here presumably mean field works, and I can understand maybe because there are infinitely many large number of species or whichever. But kind of how you are sure that one dimensions is actually hard, the hardest, because it's further away. In higher dimensions, it's more mixing. So your species will go more mixing. And actually, condition could be totally spatially uniform, but still, they develop some fluctuation-dominated, things. And even approach to steady state, typically, if of course if there is approaching to extinction, but even approach to the steady state is also dependent on dimensionality. In one dimension, in some sense, the largest deviation from mean field. But obviously, in your case, the dynamic of mean field is somehow good. So how you?
So what I would say is that what you have really the way it works is that as in terms of S for a finite size system and a finite time, you can always write essentially any correlation function that you seek to compute as a path integral with a Laplace approximation in S. So the action is proportional to S. And that you can always write it due to the structure, because the interactions over which you're doing mean field, it's not space, you're not doing mean field over space. The interaction structure is fully connected. So I would say that this is the rule of thumb. Then there is a question of what happens.
Interactive species, they are in more or less the same spatial position, right?
Yes.
Of course, if you and you fly away from me, so they are not interactive.
Yes. Okay, so to show that, and that's very generic, the solution of free exhibit scale free behavior. We can proceed by assuming, so that's going to be for the sake of contradiction, that the correlations of delta G are exponential like. So we're looking for a solution to this equation, and let's imagine that our first guess is like, okay, I'm going to look for something that falls off exponentially at large scales. And then we're going to see that this is inconsistent. So because the single species model for a given value of G bar, in that case, the single species model, where this guy is short-ranged in both space and time, belongs to the DP, directed percolation, universality class. And the intuition is that when you go close to what would be an extinction threshold, and you have a short range noise which is square root n, and a short range noise which is n, So effectively, the physics is dominated by this one. So, for instance, to show that this corresponds to an irrelevant perturbation, there is not the only word, but there is this one, thing, where what I mentioned is one of the byproducts of their analysis. So it's Physica 8, and it's 98, I think. And so now, for a given value of t, there exists a critical growth rate, G bar C. So I don't know it because its exact value would depend on the exact correlation function that I take for delta G. So I don't know it, but I know it exists. Such that, so in the steady state, n G bar is equal to 0, or G bar smaller than G bar C, and n G bar larger than 0 if G bar is larger than G bar C. And the other thing that we know from the study of the directed percolation in your safety class is that as the extinction threshold is approached from both, correlations, so as you approach the critical point, correlations of population sizes decay over length and times that become arbitrarily long.
Sorry, what is length?
What do you mean, what is length?
But are we still on the physical activity here?
No. Here it's finite dimension. It's dimension D.
Dimension D.
Yeah, it's dimension D. Yeah, sorry. So I thought I had mentioned it. If I didn't mention it, that's my fault. It's in dimension D. For now, any dimension. Okay. And in fact, so this fact as G bar approaches the critical threshold, this can be summarized by, at large scales, the scaling function G bar minus G bar C to the power 2 beta times f, where f is some scaling function, x divided by t divided by tau, where the correlation length diverges as G bar minus G bar C to the minus nu, and the correlation time diverges as G bar minus G bar C to the power Z nu. Minus. Oops. And so the exponent beta, mu, and z are characteristics of the DP university space. What's interesting is that this is enough to show that the assumption of exponential-like correlations for this effective environmental noise that is generated by species interactions is inconsistent. This shows the inconsistency of assuming exponential-like correlations. Because if you remember, so what I want is that the correlations of the noise delta G are equal to the average over G bar of the correlations of this guy. So what I want to compute is this. And in the case that I'm looking at large scales, so it's large scales, this is going to be dominated by the vicinity of this critical point, because G bar is a Gaussian variable with positive variance, so you will have degrees of freedom that lie arbitrarily close to the critical points once S is set to infinity. So what you get is with G bar C at large scales plus infinity dg bar dg bar times G bar minus G bar C times the scaling function of x G bar minus G bar C to the power nu times T G bar minus G bar C to the power Z nu. And so what you get, you can do the change of variable, and you get P of G bar C at large scales, x to the minus 2 beta plus 1 times G of C x Z minus Z, where G of y is equal to 0 plus infinity du u 2 beta f u mu y u z. So if you assume that things are full exponential-like, you plug back then into this integral that is supposed to give you delta g, which is your starting point, and then you find something that over the correlations at large scales.
You lost 2 beta in the first step.
Sorry?
G minus.
Yes, thank you. G minus 2 beta. And this, crucially, that's what I was saying. Crucially, this is different from 0.
This allows you to use the GP results.
Yes.
And then it's by contradiction. So it's
Exactly. Right.
Results cannot be short.
Yeah, then it cannot be shortened. So that shows that generically fluctuations, and then I'll just finish already because it's going to be time. But generically, that shows that fluctuations are scale fit at large scale, fluctuations of population sizes, at least over a range of times and distance that don't scale with S because it's large and finite. Now there is the question that when you define this behavior, you can ask, okay, if I put this back as a correlation for delta G, and redo the same analysis, what do I get? Do I get something that is consistent with this? So now what you need to look at is the robustness of the directed percolation universality class in the presence of environmental noise that has power law correlations. And that can be done. And the result is the following, that using, because beta, nu, and z, we know them numerically. So using numerical estimates for beta, nu, and z, we see that this is consistent with dp in dimension 3, which points toward the fact that this, but that's only a conjecture for the moment, might be the correct results in dimension 3. But these correlations are too long range in dimension 1 and 2 to preserve the dp universality. And now you flow to another fixed point step that we don't know yet. And I think it's going to be time to conclude here. Maybe one last thing that I'd like to mention is that, so there is something that is a bit confounding in ecology, that many different mechanistic models can yield similar, if you look at static quantities, distribution of abundances, for instance, many different models can yield similar distribution. So it's not a very good indicator for discriminating what would be the leading mechanism in this case, just looking at static quantities. This might point towards a way to systematize the investigation of many species dynamics, but with spatiotemporal data, which we are still lacking. One thing that is interesting is that there is one field in which we start to, we have some data like this, which are for tropical trees, where they have very long and systematic study saying that that place at that time there was one tree of that species, and you can start computing these correlation function. And indeed, so in one island, which is called the Barrow Colorado Island, there has been investigation showing that the distribution of the most abundant trees in this island, because that's what they have enough data for, indeed the cluster size is scale-free. So there are indications that maybe there is something like that, but I don't want to overcommit. It's far too early to say anything like that. But I find it interesting. And I will conclude here, and thank you for coming to this series of lectures.
Merci à toi.
Avec plaisir.
Avec plaisir.
Question? Question?
Can you map your equations to some microscopic models, like generalizations of the game of life, let's say? And can you map then the parameters and compare the behavior?
You mean to something that could not be a field theory from the beginning?
Something based on individuals.
In principle, it's doable. All these things, field theories can be obtained once you start with discrete models of population sizes or population dynamics with individual base models. You can do what's called IPhT theory for them, and you can inherit. Then you get a continuous field theory. You get a mapping in terms of a continuous field theory, where you know the microscopic parameters because it's exact. At least you have the field theory on the lattice itself, where the agent-based model is defined. And in some cases, namely if the interactions of the microscopic models are at most two-body, then you can write an effective Langevin-like equation describing that field theory. So that would look like the one that I had written, that is dtn is equal to Laplacian n plus square root n times noise. So in that sense, that's possible. I don't know. Let's say that. Those field theory can already. To investigate all that you can already do numerical simulations directly by discretizing the field theory that you've postulated from the beginning. And I would say that that's where most of the work lies. But then in principle, it's possible to.
Depends on the case, but it's better in some of these problems not to go to any field theory.
Yeah, I agree.
Really consider a microscopic model. And for instance, partially the question I asked, but for instance, if your particles, simplicity, they do diffusion, they just, in one dimension, they can be Brownian motion, but generally in d dimensions, better they somehow, like on lattice. And then, for instance, they can't coexist. So if you jump on the occupied side, they both kill each other. Yeah. And so in that case, for instance, mean field doesn't work. You write mean field like n dot equal minus n squared, and that doesn't work.
Yeah, I completely
In
agree.
1D and in 2D it's almost work, but doesn't. But in 3 and high dimensions it does work. It becomes good. But in 1 dimension, sort of better mean fieldish like that, it would be n dot equal minus n cubed. And in your case, you have, many species for sure, but you, for instance, still, started with equations which involved minus n squared, that kind of interaction. And if it was interaction was because of their kind of eliminating each other, they can coexist. For instance, in that case, for instance, in 1D, but again, I'm not sure about many species, but for one species, it would be better to consider minus n cube rather than minus n squared. And so how is your region, whichever field theory would be, God knows. So in principle, in that place, particularly, for instance, where, mean field, not mean field is kind of coming out. But in case dynamical mean field, many species really hard to say. It also, it's kind of more into your face when, for instance, they each other and density becomes smaller and smaller. If the approach to steady state approach might be a little different depending on dimensionality, but it's typically less.
Yeah, because if the approach says, if you start to have many particles in the steady state, usually you can do these Gaussian approximations with the noise that is square roots. And this is essentially what fails when you want to write a field theory for a plus a goes to 0 in 1 dimension.
But for a lot of even mathematical work, rigorous work, or for other kind of things, so people who love field theory, they use it IPhT, but essentially small group of people, and essentially they never found anything which wasn't proven. And even sometimes clean result because it's involves some uncontrolled approximations with IPhT. It just seems just a place for love of field theory to do it, and it has.
In no dimensions.
They have critical dimensions.
In no dimensions.
Yeah, well, for instance, in some of the simplest process, Carty came and started doing some things in the 90s. I would say he didn't discover anything new, and a few things he discovered, then he retracted because it turns out that from RG, from whichever, that it just useful, over there. But sorry.
The one thing that I would rely on here is that the field theory that you write here for a single species with this minus n squared, right? And absorbing to survival phase transition that you would have in a particle-based model with particles that hops on the lattice and that can, essentially reproduce and annihilate when they meet. Then this has the same critical properties, which are both P. So in that sense, I would tend to trust it.
Yeah, and there are counterexamples. Yeah, I agree with what you said.
But there are counterexamples.
IPhT, for example, works well.
No. Actually, one thing which is trying where RG gave some new results, was only in this population dominated things. When there are few species, they kill each other all, and actually the work of people which you kill us. So that's I'm not sure. So it was in early 2000, 2001, 2002. So they, it was something investigated before them, but numerically, and they found something really using Arnoulx. So if you, of course, work very hard and you are hit hard, so you may succeed.
Merci.